All right, let's take a look at section 10.4, which deals with the thermodynamics of halogenation. So halogenation is nothing more than taking an alkane and adding a halogen to it, whether it be a fluorine, a chlorine, a bromine, or an iodine. And it says if you want to determine whether or not a process is product favored, if the reaction works, you have to look at the sign of delta G, right? Gibbs free energy. We know that if Gibbs free energy is a negative number, then the reaction will be spontaneous. And if Gibbs free energy is a positive number, the reaction is not going to work. It is not spontaneous. Now, when we look at a halogenation reaction, we're starting out with our alkane plus a halogen. So we have two molecules. And then we're producing the haloalkane plus a molecule of HX. So we're ending up with two molecules. That means that the entropy term can essentially be ignored because our change in entropy, delta S, is going to be close to zero, right? Because you have two things here and two things here. So the change in disorder or randomness is really small. Therefore, the only thing that we're going to look at when we're talking about whether halogenation is thermodynamically favored or not is delta H, the change in enthalpy. And thus, we're going to say that the change in Gibbs free energy is essentially equal to the change in enthalpy. Where do we get the change in enthalpy? Well, the change in enthalpy is actually affected by a few factors, but it's mostly affected by bond dissociation energies. Let's look at some bond dissociation energies. On this table, we have the bond dissociation energies for each one of the bonds that can be broken and formed in the halogenation of methane using fluorine, chlorine, bromine, or iodine. You can see that the carbon-hydrogen bond strength in methane, of course, that never changes. Then we have the halogens, fluorine, chlorine, bromine, and iodine. We can see that from chlorine going down to iodine, they get weaker, but fluorine is in between bromine and iodine. Then you have the carbon-halogen bond strengths here, and you have the HX bond strength, so HF, HCl, HBr, and HI. Well, let's say you want to calculate the delta H for, I don't know, let's just pick one. We'll pick for fluorination, okay? So you want to pick or calculate the delta H of reaction. So let's just do for fluorination. And so we'll pick fluorination. So we'll pick F, we'll just write here fluorination. So the bond dissociation energy of the carbon-hydrogen bond is 435 kilojoules per mole. For the fluorine-fluorine bond, it's 159. I'm going to leave the units out just so I don't run out of space here. For the carbon-fluorine bond, it's 456 kilojoules per mole. And for the HF bond, it's 569 kilojoules per mole. The formula that we used was bonds broken minus bonds formed. That was what we used back in chapter 6. We said that the delta H of the reaction was equal to the bond dissociation energies of the bonds broken minus the bond dissociation energies of the bonds formed. These are the bonds that we're breaking, and these are the bonds we are forming. So forming will be the green ones, and breaking will be the blue ones. Okay, let's put in some numbers. If we put in 435 plus 159 kilojoules per mole, and we subtract 456 plus 569, and all of this is in kilojoules per mole. I'm running out of space here, but anyhow, hopefully you get the idea. We end up with a number that is negative 431 kilojoules per mole. Thus, you can see that the fluorination of methane is thermodynamically favored, right? Because if delta H is essentially equal to delta G, you get a negative number. And we know that when delta G is negative, you have a spontaneous reaction. So this is going to work. If you go ahead and calculate the delta G for all of these reactions, you see the negative 431. This is the one we calculated. You can do the math for all the other ones on your own time if you want. But you see that you end up with a negative delta H exothermic reaction, so that means thermodynamically favored, for fluorination, chlorination, and bromination. You notice that if you do the same math for iodination, it doesn't work because your delta G, since delta H is equal to delta G, or approximately, is a positive number. And so since it's not negative, there's nothing you can do about it. You can just say, will not work, because it's thermodynamically disfavored. Again, fluorination, chlorination, and bromination, these are all are thermodynamically favored. All of those can work. However, the only two that we're actually going to use be chlorination and bromination. And to get it down to the bare bones, bromination is what we're going to use most of the time, and I'm going to explain why that is. To summarize, the fluorination is so exothermic, it's not practical. If you go on YouTube and you look up dangerous chemical reactions, oftentimes they involve fluorine. I mean, it's the strongest oxidizer, so that could cause explosions and fires. And like I told you during the break, chemists generally frown on that kind of thing. We don't think about, oh, I'm trying to create a life-saving medicine. I hope there's an explosion somewhere along the way. We generally like to avoid those kinds of things. Chlorination and bromination, both reasonable. And then we get down to iodination. And since it's endothermic, it's not going to happen. Okay, it doesn't even work. So we can forget about that one. Well, let's move on from there. And let's talk about the whole chlorination and bromination thing, because they're both possibilities, right? They can both work. So now what we're going to do is we're going to talk about chlorination. So that's reacting an alkane with Cl2. And bromination, that's reacting a halogen with Br2. And we're going to look at the two propagation steps. What were they? Number one was hydrogen abstraction. Number two was halogen abstraction. So two separate steps. And we're going to compare the delta H's for hydrogen abstraction of using a chlorine radical or a bromine radical. Notice that if you use a chlorine radical, the hydrogen abstraction is exothermic, so it's thermodynamically favored. But with bromine, it's endothermic, so it's thermodynamically disfavored. Then you go down to the halogen abstraction, and they're both negative. They're both exothermic. They're both thermodynamically favored. If you tally up both of these steps, so propagation and termination, what you get is that the net reaction for either one is exothermic overall. However, what's the caveat? You know, in Sesame Street, that song, one is not like the other. Well, hopefully you noticed that the thing that's kind of the outlier is this number here. Everything else is negative. The only thing that's positive is the first step of bromination. The hydrogen abstraction for bromination, the hydrogen abstraction for bromination is endothermic. And that is actually why bromination is so much more useful than chlorination. So that's kind of what we're going to unpack now. Bromination is slower because if the hydrogen abstraction step is endothermic, that means it has a higher activation energy, right? This is the first step of the reaction, going from the starting material to this intermediate, going from the starting material to this intermediate. This is the hydrogen abstraction. The next step is the halogen abstraction. All right, you can see that this is exothermic and this one is endothermic. So obviously the bromination, right, and that's this one right here, bromination is going to be slower, right? We've got our Br2 on this side and we've got our Cl2 on this side. Hopefully you would all agree with me. Give me a thumbs up if you just say the first step looks like a much bigger uphill climb with bromination than chlorination. Okay, cool. So this is why bromination is so much more selective, because that first step is so high energy. You remember the Hammond postulate, which states that the structure of this is going to more closely resemble the transition state. So let's take a look. It says, if you have a substrate that's more complex than ethane, you've got multiple sites where you could halogenate. This is just propane here, okay? It's not anything fancy. But how many types of protons do you have in propane? You've got 6 protons in methyl groups, and then you have 2 in this methylene. So the ratio is 6 to 2 or 3 to 1. So you would think if you were to take this and treat it with Cl2, that you would get 3 times as many chlorines being on the end, exchanging for a hydrogen than you would in the middle. But what we see is something that's a little bit different than that. So let's check it out. What you see is that you actually end up with more chlorines in the middle. Well, how could that be? If there's only 2 hydrogens there and there's 6 hydrogens on the end, why would you only get 40% of this? Well, it's because if you look at the activation energy to form the secondary radical, which would produce this, let me use the right color here. This would be the secondary radical is going to form this product, 2-chloropropane, and the primary radical is going to form 1-chloropropane. We can see the secondary radical is more stable than the primary radical, so its activation energy isn't as high. It's going to form faster, and you're going to end up with more of the chlorines being put in the middle. But if you look at bromination, since that first step is such a humongous uphill climb, it's going to be even slower. It's a more sluggish reaction. Why? Again, it's got a higher activation energy, and since it's got a higher activation energy, there's an even greater difference in the relative energies of the transition states for bromination. Check it out. You see that if you treat propane with bromine, you actually get almost entirely 2-bromopropane and very little 1-bromopropane. So we say the bromination is extremely or more regioselective. And the way that we can explain that is using the Hammond postulate. You've forgotten the Hammond postulate? Let's take a look. It sounds fancy. It's nothing that's that big a deal. Look, just focus on that first step. Okay, so what you're seeing here, both of these are just the hydrogen abstractions. What you're seeing here is nothing more than this. And what you're seeing, pardon me, I'm going pretty fast here. What you're seeing here is this. Okay, that's what we're zooming in on. Nothing more than that. Okay, well, let's go back. Where was I? Okay, so for the halogen abstraction with chlorine, so I'm going to have to delete this here. But anyhow, you see that the transition state is very close in energy, or is closer in energy to the reactants than the intermediates. Therefore, the transition state has very little radical character. So if it has very little radical character, it's not going to be affected by the stability of a radical. Whereas, according to the Hammond postulate over here, the transition state more closely resembles a radical. And we know that a tertiary radical is more stable than a secondary, is more stable than a primary. So the transition state here is going to be much more affected by radical stability. And that's why bromination is so much more selective. The transition state resembles the products for bromination, whereas in chlorination, the transition state just resembles the reactant. So it has very little radical character. Here's another way of looking at it. The transition state with chlorination, you can see that this bond between the carbon and the hydrogen, it's only starting to break. It's very little, radical character at all. But when you go to the transition state here, it's almost broken. This thing is gone. So the radical stability means something, or it means a lot more than it would over here. And that is why bromination is so much more selective. This is it put in words here. It says for bromination, the stability of the transition state depends on the stability of the carbon radical. For chlorination, the stability of the transition state doesn't really depend on the stability of the resulting carbon radical as much. It does to some degree, but not nearly as much. Give me a thumbs up if you're with me so far. Even if you're with me 60% of the way and you're like, you know what, I'm going to have to go back and read this on my own. Everybody has to go back and read this on their own, okay? There's nobody who doesn't have to go back and just rehash this their own self. So now, again, this is just the first step. Hydrogen abstraction, hydrogen abstraction. This one is for bromine. This one is for chlorine. So check this out. If you look at the difference in energy of the transition states for the hydrogen abstraction, for chlorination, whether you form a tertiary, secondary, or primary radical, the difference in energy of the relative difference in energy between the transition states isn't all that much. You go over to bromination, you got a huge gap in the relative energies of the transition state. So which one's going to win? This one's going to win by far. It's so much lower, and you end up producing something that's more stable. Whereas here, it's going to be like, yeah, I guess this is better, but I might make this or I might make that. So you end up with chlorination everywhere, whereas you only end up with bromination where it's going to form the most stable radical. That is what's going to be preferred. Therefore, this is a summary of everything you just learned. What are the types of protons that we have in isobutane? We have this quaternary proton here, that quaternary carbon there, tertiary carbon, then you have these ones here. If you ripped off the one in red, you'd form this radical. If you ripped off the one in blue, you'd form this radical. Well, obviously the one in blue is a much more stable radical. So the bromine is going to add where the blue radical is almost exclusively. And none of the time is it going to end up where the red radical is. Whereas in chlorination, there's very little difference between these in the transition state because it mostly resembles this to begin with. So you end up with a mixture. It is selective, but let's face it. If you wanted to add a halogen to this carbon, which one would these methods would you pick? You would pick bromination, of course, because you get a much higher yield. You don't have to worry about separating anything. So I would say that this bromination has a greater synthetic utility. And you can imagine that by now you know that in every chapter in organic chemistry from now on, we always end up on synthesis, right? We always end up learning a bunch of reactions and then figuring out how to make a molecule with them or how to build a molecule with them. So this is going to be a very effective reaction for us, bromination. Whereas chlorination, not nearly as much. If you look at the the relative selectivity for fluorination, chlorination, and bromination, you can see that fluorination has no discrimination whatsoever. It just goes anywhere. Fluorination is a little better, kind of a 5-to-1 ratio. But then if you go to bromination, I mean, if you have a tertiary carbon, that's where all the bromine's going to go. You're going to have so little of this and this, you won't even see it in an NMR. If you run an NMR on the product, you will not even find it in there. All right, so that means you don't have to purify. And again, it's much more useful for synthesis. Well, with all that in mind, let's try a practice problem. It says, if you took these compounds, it says predict the major product obtained upon radical bromination of each of these. So let's say we took A, and we treated this with bromine, and we shone some light on it. Where is the bromine going to go? I'm going to highlight a few places. I'll put one here. I'll put one here. I'll put one here. And I'll put one, I don't know, here. Where would the radical go? Could anybody tell me? Absolutely. Luke says it's going to go where the red proton is, and he's 100% correct because that would produce the most stable radical. It's going to produce a tertiary radical. That will be your intermediate. And so upon bromination, you end up affording this product. All right, let's try the next one. What if I put a proton, I don't know, here? I'll put one here. If I put one here, and I put one, I don't know, here. Could anybody tell me where the bromination would occur on this molecule? What about this one? Would it be where the red, the black, the blue, the green? Where would my bromine land? It's going to end up where, yes, absolutely, yes. Thank you. It's going to end up right where that red proton is again, isn't it? Because you end up with the most stable radical. Here you go. So that would be your intermediate, and then you form the brominated compound, just like that. There you go. So that's why bromination is so useful. The only time chlorination is really useful, I'll show you right now. If you have a molecule that's completely symmetrical in all directions, like let's say you had, let's say you had cyclopentane, for example. If you treat that with chlorine, and light. Well, there's only one type of proton in here anyway. Every proton is equivalent, so you would only end up with one possible product, right? Like that. However, let's say you had something like, 1-methyl cyclopentane, then you're in trouble. Chlorination is not going to work because you're going to end up with, and I don't have space to draw it, you're going to have a chlorine here, you're going to have a chlorine here, you're going to have a chlorine here, you're going to have a chlorine here. So you end up with a lot of possibilities on that one. So not very useful. Did I miss a carbon in there in the chain for B? So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I don't. 1, 2, 3, 4, 5, 6. Oh, okay. I see. Yeah. Add one there, and we'll add one like that. Good. Thanks, Tracy. What do you think of the chlorination? Does everybody follow me on that? How chlorines can just go everywhere where there's a unique carbon-hydrogen bond? Okay, cool. All right. So now we've settled that. Look, I can even show you something else here before we go into stereochemistry. Like if you go down to the end of the chapter, where am I here? What we just covered, this is one of the major thoughts of the entire chapter, is that reaction. And then it's shown right here. This is a reaction we already covered, and this is one we're probably going to look at in our next lecture. But let's go back to section 10.6. We can cover a little more ground here. And I can show you just a little bit about stereochemistry because we've already covered the molecular geometry of a radical this morning. Could anybody remind me what the molecular geometry of a radical was? What we said it was? In Chemistry 3101, what's the molecular geometry of a carbon radical in this class? Exactly. Thanks, Kiana. It's trigonal planar, isn't it? Right. So you can imagine that with 2-chlorobutane, if you make a compound like this, it could be R or S, and you actually end up with a mixture, right? Because when you make that radical on the secondary like this, if you make this radical as your intermediate, remember that this is trigonal planar. So that means the chlorine radical, it can come in from the back or it can come in from the front. So you actually end up with a racemic mixture. Racemic mixture. I like that. Now there's no stereocenter here, so you don't have to worry about that. But if you form a stereocenter, because we treat our radicals as being trigonal planar, again, if you have a radical, it can come in from the top face of the molecule. I don't know what I did there. It can come in from the top face of the molecule like that, or it can come in from the bottom face of the molecule like that. And that's why you end up with a racemic mixture. So if you try to chlorinate butane, you end up with 3 possible products. You get a racemic mixture at carbon number 2, and then you also end up with 1-chlorobutane as well. Hey, let's do a little final exam review. If I zoom in on this one here, could anybody tell me, is this one R or S? Let's practice. I'll have a sip of coffee while you're taking a look at it. I know you've all been working hard on your stereochemistry. Yeah. Yep. You guys are good. Very good. Excellent. 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 Yep. All my students are 100% correct. Yeah, it's S. Absolutely. The hydrogen's in the back. Chlorine's number 1. Ethyl group's number 2. This is number 3. It's going that way. So it's S. Yep. So that would be S2-chlorobutane. Great. Excellent. That's chapter 5. That's weeks ago. You're still crushing it. So that's good. Let's see here. So in the halogenation, this is another one. Like, let's say you have a chiral molecule like this. This is S3-methyl hexane. So S3-methyl hexane. If you brominate that, the thing is that you destroy the chiral center, right? Because this is where the hydrogen that's going to be abstracted is. So you end up passing through this intermediate, right, like this, and then you end up destroying the chirality center, you know. So now the bromine can come in and attack from either face. So that's kind of crummy, because if, let's say, you worked really hard to make a chiral molecule, then you lose all the chirality. But hey, that's what happens, okay? So you just need to be aware of it. It's just the kind of thing that, as a synthetic chemist, it makes me cringe a little bit. You have a chiral center and then it vanishes. Usually not a good thing in chemistry. All right, so there's that one. Hey, let's try one here. It says predict the chemical outcome of the radical bromination of the following alkane. So let's say we take this compound here. We have a chiral center, and that's where our tertiary carbon-hydrogen bond just happens to be. So if that becomes abstracted, we end up destroying that chirality center, don't we? It's not a chiral center anymore. And so now the bromine can come in and attack from either face. I guess I need some reagents. So the bromine can attack from either face of the molecule, and you would end up with a pair of enantiomers in this case. So you'd end up with the methyl group going up, bromine going down. I'll just put plus enantiomer. So that's, you know, a chiral center that bites the dust. And the next one, you've got two chiral centers in it. And something similar is going to happen. You've got bromine and light. This is the hydrogen that's going to be abstracted. So when you rip that thing off, then you destroyed the chiral center on the left-hand side here, so to speak. And you end up with your tert-butyl. You didn't do anything to that or to this methyl group. But now the bromine can come in from either face of the molecule. So you can end up with this compound where the tert-butyl is not going to change. The methyl group is going down. You got this methyl going down. You get the bromine coming up. Let me see if I can copy and paste this. So you end up with this compound where you just move the bromine down here. Could anybody tell me, and it's not a trick question, just what would be the relationship between these two compounds? How would you describe their relationship after learning, or after chapter 5? They're a pair of, yeah, absolutely. They're diastereomers, aren't they? Because they have the same chirality at this chiral center, but they have the opposite at this chiral center. So yeah, they're diastereomers to each other. So we'll scribble that in here. Diastereomers, stereomers. Yep, great. Excellent, excellent, excellent. Let's cover one more section today. One more section, which deals with, let's cover one more section. It's called allylic halogenation. So allylic halogenation, we'll just go over it quickly here. It says, recall that the weakest carbon-hydrogen bond, the one with the lowest bond association energy, is going to undergo radical hydrogen abstraction faster than the others. So an alkene, if it's got an allylic carbon, that's where the hydrogen abstraction is going to occur. So we've got a proton in red, blue, and green. This is the allylic one here. So this is allylic. And so this is the weakest bond. The other two are stronger. So if I'm going to form a radical anywhere, it's going to be there, right? Because you end up with a radical like this that is resonance stabilized, and you should be able to draw the resonance structure like that. I'm not going to go over the entire thing right now. But allylic carbon-hydrogen bonds are going to be weaker than vinylic or just a secondary carbon-hydrogen bond. So you get this resonance stabilized allylic radical. All right, so bromination is actually going to be selective for the allylic carbon. But if you look at this reaction that I have on the slide here, and I took this right out of the textbook, if you brominate cyclohexene, you can get allylic bromination because that carbon-hydrogen bond is so weak. But if you're thinking, well, hold on, Mr. Dan, didn't you teach me that if I took cyclohexene and I put it in bromine, like, didn't we even look at that this morning when we were, doing some practice? We said that adds across a double bond in an anti-fashion to give you this. Like, what gives? Like, what's going on? Why are you doing two different reactions? Well, the problem is you would also get this plus its enantiomer as well. And that is not super handy. So instead of doing this, we have a workaround for that. And what we do is we use this new reagent called NBS. So NBS stands for N-bromosuccinimide. So you can imagine that succinimide is just this. So it's a derivative of succinic acid in here. That's neither here nor there, but this is succinimide. And then if you add a bromine on the nitrogen, it's called N-bromosuccinimide. It's a really easy compound to work with. It's a solid. It can be crystallized from water to make it super pure. But it's a good source of bromine radicals because when the nitrogen-bromine bond breaks in the presence of light, you end up with this radical that is doubly stabilized, right? On the nitrogen, you could draw the resonance structures here if you want. I'm not going to do that right now, but it's a good source of bromine radicals. So what it does is you get a bromine radical, but it keeps the concentration of HBr and Br2 very low. So you're not going to get hydrohalogenation on the double bond, and you're not going to get dibromination or bromination of the double bond. You avoid that. You just have a little bit of bromine radicals kind of floating around. And so it's going to, the bromine radical will abstract a hydrogen from the allylic position to form your allylic radical. And then you only make a little bit of HBr, right? You'll only make HBr when this happens. And then there's a mechanism that's not even covered in our textbook, but it says what happens is that this HBr that's made from that first step, it reacts with the NBS. So they do a reaction together and you make bromine, Br2. You only have a little bit of bromine around, but that bromine is not in the presence of an alkene. It's in the presence of an allylic radical. And so the halogen abstraction occurs and you end up doing the allylic bromination. So that's why we use NBS and we don't use bromine. I'm probably not going to ask you on a quiz about all the mechanics of this, but in the homework, I would say it would be fair, you know. But probably in a quiz, I won't be going on, like, explain to me everything about, you know, allylic bromination. So if you have an allylic carbon-hydrogen bond and you want to brominate that, you just use NBS, okay? Nothing else. Just use NBS and light and it's done. However, when you do that, the problem is if you make a radical, an allylic radical, what do we know? It can participate in resonance. So you can end up with two allylic radicals, and so you can end up with mixtures in that case. Okay, remember, it's not rearrangement, it's just resonance. These two are resonance structures. So in that case, you could end up with the bromine here, or you could end up with it here. You have to be aware of allylic bromination can cause, you know, or can form regioisomeric products. So why don't we end today by looking at a problem and see if we can figure out if we end up with regioisomeric products, yes or no. Let's take a look at B. It says, predict the products when each of the following compounds is treated with N-bromosuccinimide and some UV light. So with B, we have our NBS, N-bromosuccinimide, and some light. In this one, we only have one kind of allylic hydrogen. It's this one here, right? There's no hydrogens on this carbon. So the only place you would do a hydrogen abstraction would be here. That would produce this allylic radical. Let's draw the radical like this. Here we go. And like that. Oops, where's my carbon? I lost it. There we go. So even if this undergoes resonance, you still end up with the exact same thing. Okay, there's no difference between, oops, I drew my double bond in the same place. You end up with no difference at all between the two. Is everybody with me that these two are identical? Because we have free rotation around this carbon-carbon bond, you can't differentiate between these two radicals. Like if I brominate at either position, I get the same molecule. Okay. So I don't have to worry about these two radicals. I can just draw one of them. So I'm going to delete one of them. And let's leave it in. And we'll just say, okay, well, the bromination is going to occur at that position. So I'm going to end up with something that looks like this, where I have my double bond, my bromine's going to be here. I have my geminal dimethyl, and there we go. So this would be the product. We'll put here only product. Okay. What about the next one? You can see that there's not a plane of symmetry, but there's rotational symmetry in this molecule around this axis. If you were to rotate it 180 degrees, you wouldn't be able to tell it apart. So the only kind of allylic hydrogen we have is this one here. If we were to abstract that, NBS and light would end up with a radical here. It's allylic. And does it have a contributing, another resonance contributor? The answer is yes. So we could draw this. And now we're going to draw the other resonance contributor, which looks like that. Okay, like that. So we've got our radical here. And now our bromine can add at either of those sites. So we can have the bromine at this position here, or we could add the bromine at this position. Either one. So we end up with a mixture, don't we? And if you look at these, the second one, the one I'm drawing right now, it's got a chiral center in it. So here you'd end up with a pair of enantiomers for this one. We'll put here, what do we put? Plus enantiomer. And, you know, as to which one is going to be formed in greater yield, this one is actually going to be formed in a greater amount. We'll put here, why don't I just put major product? So this is our major product. Could anybody guess why I wrote that this one is the major product and the other one would be the minor products, I guess? The racemic mixture would be minor, but the other one would be major. Could anybody give me a very simple explanation why? It doesn't have to be complex, I can tell you that. Exactly. Yes. Clinton told me it's because this, I'll use the green pen. This is the most stable radical. And there you have it, my friends, allylic halogenation. Now, go to the very end of the chapter, you'll see that you've covered all of the reactions already in this chapter. We covered halogenation. We said that bromination was best because it was so selective. What can you do with an alkyl halide? We looked at all kinds of substitution and elimination reactions in chapter 7. We looked at SN1, SN2, E1, and E2 reactions. And what happens if you do an elimination reaction? Well, then you make an alkene. In chapter 8, we learned a plethora of reactions that can be done with an alkene. Does anybody know what this is here? Oh, somebody knew already. So yeah, that's Pandora's box. So I put that in there. You're opening up Pandora's box of possibilities. There are so many possibilities that are opened up to us now with, you know, alkene chemistry and with alkyl halides. And now you know how to make an alkyl halide. So very important. If you look at the review of reactions, we've covered all of these reactions. Now today we covered allylic bromination in detail, and we covered bromination of alkanes in detail. What we're going to save for tomorrow will be the anti-Markovnikov addition of HBr to an alkene. I know that we covered that in detail, or we covered some of it in chapter 8, but we didn't cover the mechanism of why you get anti-Markovnikov addition. And that's what we're going to cover tomorrow. So if you go all the way up here, you can see that we only have one more section to cover. Section 10.10, it's 1, 2, 3, 4, 5, 6, 7, 8 slides plus, and that's a practice problem. Then we'll try some synthesis problems, and that's the entire chapter. So we've covered the vast majority of the chapter already.